Hello guys, in the last lecture we talked about the relation between the orbits in a hydrogen atom and how do we calculate the energy of them. So now for the start of this video, we want to talk about the wave behavior of matter. So we said light can be characterized as both particles and waves, and we talked about that in the last video. And so if light can be characterized by those things, then can matter be characterized in a similar manner? Well, using Einstein and Planck's equation, Louis de Broglie derived the formula which is lambda is equal to Planck's constant over m times v. So this one, as we said, wavelength is lambda, h is Planck's constant, m is mass in kilogram, which is important because, and v is velocity, meters per second. Well, he uses this term matter waves to describe the wave-like properties of matter. So with regards to the atom, de Broglie concluded that an electron orbiting a nucleus could also be thought of as a wave possessing a characteristic wavelength. So for example, this is an example. Calculate the wavelength. What is the wavelength of baseball, length of a basketball, for example? Weighing, for example, 142 grams, and then thrown at the speed of, basketball is not bad. Baseball, for example, it doesn't matter, it's just an example. Baseball at again 142 kilometers per hour. So what is the wavelength of this example? Wavelengths, as we said, can be calculated using this formula. So what is a Planck's constant? 6.63 times to the 10 to the power 34 negative. We said the weight is in the mass is in kilogram, so 142 gram is equal to 0.142 kilogram. So this one is 0.142 kilograms times, what's the speed? 142 kilometers per hour. So how do we convert that? So in order to convert kilometers per hour to meters per second, you just have to divide it by 36, and which in 3.6. In this case, it would be 39.4, and the final answer will be 1.18 times with a 10 to the power 34 meters. This is the wavelength of our example. So matter can also act as a wave. Then the uncertainty principle of Heisenberg comes up. The dual nature of matter, particle and waves, sometimes create difficulties with regard to the position and the velocity of an electron in space. So every time that scientists try to observe one property of a one property, it led to an inability to observe the other property. So what uncertainty principle of Heisenberg says, basically in a simple manner, says that the more you know about one, the less you know about the other. So what does that mean? For example, if you know more about the position of an electron, you know less about its velocity. And there were some debates over time about that. For example, Einstein said, so we can release two electrons with the same momentum. We can observe one velocity in the other position, but then we can conclude, because we can observe the velocity of the other one, and we don't know nothing about its position, and then we go about the position of the other one, and we don't know nothing about its velocity. We're unsure of. Then he said, okay, so we can just release two with the same momentum, so we know what happens, but that's not how it works. Every time there is a different result of it. So it brings an inability to observe another one if we want to know more about the other one. And the Heisenberg uncertainty principle is on the mass scale of like atomic particle, and the exact position, direction of motion, and the speed, the exact position, cannot be determined simultaneously. And the formula for the Heisenberg principle mathematically. So the formula for the Heisenberg uncertainty principle can be mathematically expressed as the uncertainty in the position times to the mass times to the uncertainty in the velocity is greater or equal to the Planck's constant over 4 pi. So delta V is uncertainty in velocity, and this one, delta X, is equal to uncertainty in position. M is mass, and Planck's constant, as always, is 6.623 times to the 10 with the power negative 34. And now I will give you guys an example, and you should pause the video, try to solve it, and then check the answer. I hope you guys have tried to solve this problem. So it says a proton is accelerated to 1/10 the velocity of light. So what is the velocity of light? We show it as C. It's 3 to the 10 with the power of 8. So it says 1/10 of the velocity of light. So times the 1/10 will be our V, and UV is 3 to the 10 with the power of 7. And it says, and this velocity can be measured with precision of 1%. What is 1%? 1% is 1 over 100. So our new velocity is 3 to the 10 with the power of 5. And that's the uncertainty of the velocity that we have for the Heisenberg uncertainty principle. The formula was delta X times mass times delta V greater or equal to Planck's constant over 4 pi. Again, precision of what is the uncertainty in the position of this proton? Mass of proton is 1.6 times to the 10 with the power of negative 27. So we calculated our V, delta V. So this one is our V, and this one is basically our delta V. So now our delta X, we have to make it alone. So our delta X is greater or equal to this one. We should divide by that one, by the M to the delta V, and divide this side too. These cancel each other out, and then the whole formula would be H over 4 pi M delta V greater So now we calculate it, and it would be 6.63 times the 10 with the power of negative 34 over 4 pi 1.61. It's not working. 1.6726 times to the 10 to the power 27 times to the 3 in times to the 10 to the power 5 should be one greater equal to 1.05 times to the 10 with the power of negative 13 meters. That's the uncertainty in the position of the data that we have. And now we can go to the quantum mechanics in atomic orbitals. So the wave properties of an electron can be described mathematically from the Schrödinger's wave equation. And well, when we solve the Schrödinger's equation, it leads to a series of mathematical functions called wave functions. And we usually show the wave functions like this. That's how we show the wave function. Well, this one gives no information about the path of the electron, because energy and position are also complementary properties. It just provides a description of the electron's matter wave in terms of position in 3 dimensions. So when we talk about the square of the wave function, like this one gives the probability of finding the electron at any point in space. That's how it works. And then when we find the probabilities at various points in space, it would also be possible to construct a probability density plot. And so the most for the 1s orbital, the probability of having I can show you this. So that's the probability density on the y-axis, and r in the x-axis. So you guessed it right. As we go further from the nucleus, the probability of finding an electron would be less and near 0. It's not always 0, it's near the 0, and this one goes to infinity, but it's not go to infinity. There's always something. This one going to reach 0, but it doesn't. And the height of the curve is proportional to the probability of density. And then if we introduce the orbitals and quantum numbers, so there are 3 quantities that are called quantum numbers: n, l, m, which are involved in the wave equations. So a specific set of values for n, l, and ml, let's say ml, corresponds to the electron orbital. So let's talk about the n. N is principal quantum number. It's called principal quantum number. The values allowed for it are integers, like n can be 1, 2, 3, and so on. And what it describes size and the energy of an orbital size of orbital, and to get the values of n, the greater distance from the nucleus it has, the greater the value of n, the greater the energy, and that's it. And now we'll go for L. L is angular momentum quantum number. So L, angular momentum quantum number. And the allowed values are n minus 1. So basically, when we start by 1 for n, so L would be start by 0, 1, so on. And so let's show it like this. We put letters for the L, and it's like this. For 0, 1, 2, 2 and 3, these are the L values. There are letter used, so we use S for 0, P for 1, D for 2, and F for 3, the letters. And then we go to the magnetic quantum number, which we show as ML. And the allowed values are from negative L to positive L, including 0. And so what it shows is this specifies the permitted orientation in space of the orbital. And there are some definitions you might need to know. For example, electron shell is the collection of orbitals with the same values of n. If I want to give you an example, for example, all orbitals that have an n equals to 2 are said to be a second shell. And what is subshell? Subshell is the set of orbitals that have the same n and L values. The subshell is designated by n value, and the letter corresponded to the value of F. If I want to give you an example again, for example, orbitals with n equals to 2 have an L equals to 1 are referred as 2p orbitals and are in the 2p subshell. So for example, as you know, we set here 1 is equal to p. We set n equals to 2. So when n is equal to 2, n minus 1 would be 2 minus 1 equals to 1. Our L will be P. And our N is 2. So they're in the 2p orbital and 2p subshell. That's how it shows. So if I want to give you general of all of what we said, like up until now, about the about the quantum things, the quantum numbers and orbitals, there's we can talk about the 3 levels. The first level, we have n equals to 1. So L is n minus 1. So L is 0. M also is positive negative of L, which is again 0. These two are 1s subshell. Sub level. Same. So as I said, principal level is specified by n. This one is a principal level. Sublevel or subshell are specified by n and L, and orbitals specified by NL and ML. The second level, we have n equals to 2. But this time, we said L is equal to n minus 1. So we have L again 0 from the first level, and we have L equals to 1. We have both of them. This one is basically 2s, this one is 2p. L equals to 0 is s, and the L equal to 1 is p. So for the 2s, again, same as here, ml is equal to 0, and ml here we said from negative to positive L, which is negative 1, 0, and plus 1. So these are a 2p sublevel, these are our 2s sublevel, and third level. N equals to 3. Again, L equal to 0, L equals to 1, and L equals to 2. Same as here, ML here is 0, ML is equal to negative 0, positive 1. But for this one, again, it goes, let me write this. Negative 2, negative 1, 0, positive 1, and positive 2. These are 3D sublevel, 3P sublevel, and 3S sublevel. And that's it for the orbitals and the quantum numbers. If we want to talk about, so let's review what we learned by now. The principal quantum number we showed is n, and it determines the energy in the energy of the orbitals and takes the integer values 1, 2, 3. Angular quantum number we show it as L and describes the shape of the orbitals and takes the values of 0, 1, 2, which is basically n minus 1. Magnetic quantum number describes the orientation of the orbitals and takes the value of from negative L to positive L. So the shape of the atomic orbitals. So there are some stuff that you can memorize. For example, for one s orbital, the distribution of electrons in an s orbital resembles a spherical shape. It's if we want to draw it, it would be if we draw a circle here, and this is our y-axis. These are our, let's call that x. I'm sorry, x. It's up to u, and this one is z-axis. So this one is for one s orbital. It's like a spherical shape. For 2s and 2p, well, as the principal quantum number increases, the size of the orbital increases too, as we talked about. The 2s and 3s orbitals contain nodes, which are the regions where there is zero probability of finding an electron. And the number of nodes can be, for a given orbital, is like n minus 1. So for example, it's like this. This one is our 1s. This one, again, same size, but there's an area here, like another circle here. And this one is 2s. Again, same size, same, and same. This one is 3s. So what are nodes? These are not. There's a zero the color ones are like the probability of finding an electron here, and these are called nodes because there is zero probability of finding an electron here. And notice that this one, n minus 1, will be 0, n minus 1 would be 1, which we have only one node here, and n minus 1 is equal to 2, and notice we have 2 nodes. So for the p orbitals, the p orbitals have like a different shape. The p orbitals have the electron density concentrating on the sides of the nucleus in 2 lobes with an angular node at the nucleus. So if I want to give you and also notice that for 1s, the m, which shows an orientation for us, where is it? Okay, it shows an orientation for us, is 0, so there's no orientation. Did you see? There's only one spherical shape for it. But for the p orbitals, we have m equals to 3, so we have 3 orientations. So how we show the p orbitals? There's only like 3 different orientations, so it's basically, if I want to draw it, it would be something like this again, like this. I can draw them later, and like this. So for example, I can draw this one by blue, 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 and red, red, red. Okay, so notice that we have only 3 orientations here, because L equal for p orbitals, L equals to 1, so m for our orientation is equal to -1, O, and +1, so we have 3 orientation. And now for, probably you guys have guessed it, for the DNF orbitals, here the d orbitals have 1, 2, 3, 4, 5 orientations. So we have 5 orientations for d orbitals, and the shape is quite different. And so if I want to just put one as an example, for the d orbitals, we have a shape like these are x, y, z. By green, and that's how they shown. Like, and there's only 5 orientation of them. And for the f orbitals, so f is L equals to 3, so ML would be -3, -2, -1, O, +1, +2, +3. So we have 7 orientations. And yep, orientations. So there's also another principle, Pauli Exclusion Principle, which is called the electron, but it basically, the title is Electron Spin and the Pauli Exclusion Principle. When scientists applied the quantum mechanics model to experimental data, they found out that it's not that right, because there was something missing. There was an experiment. They beam of like silver atoms, and then the beam goes through a slit, and then in a magnet, and the beam collector plate found out that the light would be separated into two different parts, the positive half and negative half. And so a fourth quantum number, the electron spin quantum number, ms, was assigned of possible values of positive half and negative half. If I want to draw it to like give you a better visualization of what I just said, so imagine a cube here. It's not okay. Imagine a cube here. Okay. There's a beam of silver light here, silver atoms here. This one goes through a slit, and this one is slit. So the light goes from this part and it reaches a magnet. Let me show it like this. That's our magnet. For example, this one is S pole and North pole. So when the light goes through this, it would separate into two lights, negative, positive, 2, and the sheets over there it's called beam collector plate. So the beam here splits to 2. So the electron spin quantum number was assigned here, and the Pauli Exclusion Principle says no 2 electrons in an atom can have the same set of 4 quantum numbers. So the things that come, like the consequences of the Pauli Exclusion Principle, is for the given orbitals, the values of NL and ML are fixed. So if we put more than 1 electron in a single orbital, they must have different MS values. Because there's only 2 MS value, then orbital can hold a maximum of 2 electron, and they must have like opposite spin. And so if I want to give you an example for a concept review, what is how many orbitals are present in n equals to 4? So n equal to 4 has L, 3, 2, 1, and O, called S, P, D, and F. For S, we have ML, as we said, 7 orbitals. 7 orbs. We just said orb for simplifying it. For D, we said 5 orbs. 1 was 3 orbs. This one is 1 orbs. So the total would be 16 orbitals. And you might have noticed, like, there's a 16 and 4 here. So to find the orbitals, you just have to say n to the power 2. So if your n is 4, the number of orbitals would be 16. If your n is 3, your number of orbitals would be 9. See? 5 if you have n3. 5 plus 3 plus 1 is 9. And if you have n equals to, 2, so n to the power 2 would be 4. 3 and 1. 4. And also that's it. So now we can talk about the electron configuration now, but I want to put it in another video. But if you guys have any problem with the concept that we reviewed by now, you just can email me and you just put a comment on my video and I would answer it. Please like and subscribe, and I would be happy to share other stuff with you guys.